Well, very good evening, friends. My name is Shubham Shukla, and I'm working as an assistant professor in the Department of Electronics and Communication Engineering. Today, I'm going to deal with a very interesting topic. Good evening, my dear friends. My name is Shubham Shukla, and I'm working as an assistant professor in the Department of Electronics and Communication Engineering, Kite Group of Institutions, Ghaziabad. I'm also the research scholar. I'm pursuing my PhD from the field of robotics. Today I'm going to deal with a very interesting, perhaps a very relevant topic in the field of machine learning. And the name of the topic is computational learning theory. So why we require computational learning theory? We need computational learning theory in order to make the model understand how to learn. So when I talk about model, I mean to say that we need to give a machine the way, the process, the mechanism to understand, to process, to compute, and to learn out of it. So the first part is to make the model to understand. Now, how we can make the model understand? What are the essential features which we need to give to the learning model? So the first part is, what kind of tasks are learnable? We need to identify that what type of tasks are learnable, what kind of data is required for learnability, and then what are the requirements of learning algorithm, as for example space and time. If suppose I'm talking about data, then specifically I need to be very clear that I'm talking about how much space that specific data is taking or acquiring, and how much time it is taking to get processed. Second is learning algorithm, to develop and analyze models. Now, to develop and analyze models, we need to develop algorithms that probably meet desired criteria. First, it proves the guarantee to be a successful algorithm. And in order to make the algorithm successful, we need to make an algorithm learnable. Now, what are the essential features with which you can make any algorithm learnable? So, the first task is to make the algorithm learnable. Second is, what type of data is required and what should be the size of data. Third is resource requirement, space and time. These are the two resources. Fourth point is, we should develop an algorithm under certain criteria which proves the guarantees of its existence. Now, how we can design the algorithm? So before designing the algorithm, we must keep this very important point into aspect, that there should be enough confidence present in that algorithm. So when I'm talking about confidence, then what does it signify? It signifies that how the algorithm actually works on the future data. Suppose if I want to learn anything, then how I can learn? I need to have some data. I need to have some future data. And I need to have the ability to make a generalization out of those data. So similarly goes with all those algorithms. So in order to make any algorithm feasible for learning model, we need to give that algorithm the confidence, and the confidence can only be built in by giving the model the ability of generalization. Now, how we can give that particular model the ability of generalization? So we come up with a very great idea. To accomplish computational learning theory algorithm, we require a very specific model which is known as probably approximately correct model, where P stands for probably, A stands for approximately, and C stands for correct. So if we want to learn anything, then first we need to take probably into consideration, then the second part approximately into consideration, and the third part correct into consideration. While combining all these three aspects all together, we can come up with computational learning theory, or we can make any model learnable. Now, how this PAC model actually works. Suppose this is the hypothesis space, or perhaps I can call it as instance space. So let us assume that C is the target function which we wish to learn. Suppose here this is the C, and C is the target function which we wish to learn. This is the instance space, and the instance which are within C are the members of class, and we want to learn C. In order to learn C, we have some training examples which are labels as plus and minus. These are the training examples which are labels as plus and minus. We want to come up with the hypothesis H. Now, here we can come up with the hypothesis H. So, here C is the original hypothesis, which comprises that the positive examples are within C and the negative examples are outside of C. We have sample from the instance space as the part of our training data, and we want to come up with the hypothesis H. Now, H may not be exactly equals to C. So what is error region? The error region is given by C XOR H, because here we can see that the examples present in this region as well as example present in this region are entirely different. The training sets present in this regions may not be present in hypothesis space H, as well as the training sets present in hypothesis space region H may not be present in the space region C. And that is why the error region is given by the equation C XOR H. C says that the error region, this is the error region, C says that the error region, these instances are within the concept. These instances are within the concept. Within the concept, but H does not include them. H does not include them. Suppose whatever the training data is present in this C cannot be included in H, and whatever the training data is present in H cannot be included in C. So this region is also error. C says that they are outside the concept, but H says that they are inside. So there is a bit contradiction which is actually happening. these regions are the error regions, whereas the remaining is the correct region. So this C XOR H is the error region, and we want the probability of this error region to be small. So therefore, it gives a special equation known as probability of C XOR H less than or equals to epsilon. So ultimately what I want to say is that I have drawn this hypothesis over here. There are some training data sets which are present in the C region, which are not present in the H region. There are some training data sets which are present in the H region, which are ultimately not present in the C region. So these two regions are known as the error region. Rest all the regions of the instance space are the correct regions. So in order to make this particular model valid for learnability, we need to reduce the amount of error. So when we reduce the probability of error of both the region, we can make the learning feasible. Ideally, we want H to get equals to C, but sometimes it will not be possible to get C equals to H. So we want to bound the probability that an instance will occur in this region. So a hypothesis to be approximately correct, if the error is less than or equals to epsilon, will give you this particular equation, where epsilon is the parameter lies between 0 and 1. And we can say that epsilon is between 0 and half. So epsilon is the error parameter, and if for a given epsilon the probability of this specific region or this specific error region is less than or equals to epsilon, then we say that the hypothesis is approximately equals to correct, or the hypothesis is approximately correct. There may be some situation where the learning algorithm may not give us the correct hypothesis, which is epsilon approximately. So the probability we want to bound, so in that case we need to bound the whole probability of the error region, and I have done over here the same thing. Learning algorithm give us an approximately correct hypothesis. This probability must be greater than 1 minus delta. Now, what is delta over here? Delta is called as the confidence parameter, which lies between 0 and half. Delta is the confidence parameter, and mostly the value of delta is 0.1. So the probability which we get an approximately correct hypothesis, this is called as the confidence, and this is controlled by the parameter known as delta. We can say that delta is, suppose the value of delta is 0.1, then we can say that 99% we get the approximately the correct hypothesis. And this is how we make computational learning algorithm works. Thank you. We will deal with finite hypothesis space in our next class. So for now, thank you.